2016 semester. We have an exciting semester for us. I notice Dr. Ten is not in the audience, but he's the longtime lead of what physicists do. I often tell this story, I'll tell it right now, which is I came and was looking at positions and faculty positions, and one of the things that really drew me to Sonoma State University was the combination of research and teaching that goes on here. The dedication to the students being number one, first and foremost, was very important. And I told them in my interview, I thought that the speaker series was fantastic, that having these public lecture series was just one of the best things going, when I look at this compared to other departments, that we could stay connected to this very vibrant scientific community. And they said, that's fantastic. They hired me, and I was very pleased with that. And they said, we're glad you like it, now run it. And so it's been my pleasure. And this semester we have many, many fine speakers. And not to make you nervous, but we have the first of my gets where I have gotten a Nobel Prize winner to speak in this series. And Professor Ten, Emeritus, has gotten 14 Nobel Prize winners to speak in the series. But we have a Nobel Prize winner this semester. But we're starting with a fantastic speaker, of course. It's our very own Michael Dobbs. Now, he is no pressure at all. No, we're very excited because what this talk allows us to do is see one of our students go off and do research elsewhere. And so we're starting with a student talk. So rather than bringing in someone from another institution, we sent one of our own out to another institution and to do a really amazing bit of work. He'll describe it, but I wanted to say he went off and staying here locally, he did a remote learning class. He took a class from CSU Fresno in particle physics, which is not a class that we don't offer here, and yet it is one of the areas that people study in physics. And so to get that expertise while you're here was just a really, really neat experience. And then there was a competitive program to let students who took that class get into summer research programs. And we are so very proud of Michael Dobbs getting into that program, achieving his goal of then being able to go and research at a very important, and for the general members of the audience here, to work at CERN in Europe and to work on the Large Hadron Colliders, to work on one of the major programs in science that's going on today. And so we're very thrilled, and let's give a warm welcome to our undergraduate speaker talking about his research that he did this summer. It's Michael Dobbs.
All right, so hello everyone. Like he said, my name is Michael Dobbs. Hello, Dr. Kaminsky. All right, so yes, I went to CERN, and through that program that he was talking about, so they have a program at Fresno State called CSU NUPAC, which sends 10 students per year to CERN, 5 of them not from Fresno State, 5 of them from Fresno State. So I was one of the lucky 5 that got there without being from Fresno State. And so what you do is, if you get accepted during that spring semester, you take an online class that has to do with the programming language they use at CERN, which is called Root. I ended up using PyRoot, which is a combination of Python and Root, which was nice. And after that, then you're off on an 8 to 9 week internship at CERN, and they tell you to go travel afterwards. So that'll be at the end. We'll just see some pictures. Okay, so first off, what is CERN? So CERN is a very large particle collider. And so pretty much what happens is you have batches of protons that are sent into this ring. And it starts off down here in the linear accelerator, goes into the first ring, goes into the second ring, and then is sent into the large ring. So these protons are sent 2 different directions from this large ring, from the medium-sized ring. And so they go this direction and this direction. And then they collide at certain points along the detector, which are highlighted in yellow. So what I worked on was the Atlas detector, and I worked on an algorithm that looks at data that comes out of the Atlas detector and tries to find certain events. So the protons that are traveling around here collide at about a center of mass energy of 14 teraelectrovolts, and we have about 10 to the 8th collisions per second, and that is the summation of all the different events from these 4 detectors. All right, so yes, Steve.
And what kind of protons are they? Generic?
Yes, generic protons. Yes. All right, so on that note, a proton is what we know as an elementary particle, but it is actually composed of quarks. So quarks have fractional charge because we defined +1 and -1 to be E, but now that they're constituents, they have less than 1. So a proton is composed of 2 up quarks and a down quark, and a neutron is composed of 2 down quarks and an up quark. An electron is actually an elementary particle. Thankfully, we got that one right. And also there is an electron neutrino, which is pretty much a neutral version of an electron, but it is much, much smaller. And so what we have is, this is the standard model, pretty much the particle zoo, which is all the different particles that we have in our universe that we know of today. There may be more. So what we have are up and down quarks, which compose protons and neutrons, which is what we look at in chemistry. And there are heavier versions of those, called trans and strange. There are even heavier versions of those, called tops and bottoms. And also for electrons, you can think of muons and taus as just heavier versions of electrons. And so over in this column right here, we have the force-carrying particles. So as you might know, the photon carries the force of the electromagnetic field. The gluon is what's going to carry the force of the strong field, which is how these interact, how quarks interact. And the weak force mediates decays. So that is going to be, you can think of it as how radioactive decay occurs. And also we have over here, this was recently discovered, the Higgs. This gives particles mass, and the graviton has not been discovered yet, although gravity waves have been discovered. And LIGO. And so this has not been discovered yet, because these are supposed to be very heavy and very hard to detect. All right, so what is CERN actually doing by colliding these protons? So what CERN is doing is it's looking back into the history of the universe. So when you get higher and higher energy protons colliding, what you can do is probe the early universe, which was a very high energy place. So the higher energy you get, the more particles that pop up on the past slide that were around during this time. So you can simulate what happened back then, and you can use it to find out some of the behavior that occurs at high energy. Okay, so quick summary of the fields and their bosons that mediate the forces. So we have electromagnetic mediated by the photon, the strong mediated by 8 different types of gluons, the weak mediated by the W and Z bosons, and in our standard model we do not have gravity in there at the moment. So there's no unified field theory just yet. That's what we're hoping for. All right, so when you have these protons colliding, you're not looking at electromagnetic forces, you're looking at strong forces. So there is a nice correlation between the two of them, though. So electrodynamics, which is how protons and electrons interact on that scale. You can look at electric charge causing the coupling of atoms, like protons orbiting about electrons, and those create molecules. So the same you can think of for quantum chromodynamics, which is quarks. So you can think of color charge, and that creates couples of quarks, which create baryons, which create the nuclei. And the nuclei create atoms, which create molecules. So it's like looking one dimension deeper into atoms. It's how protons are held together instead of how atoms are held together. So yeah, they're different forces, but they're very similar mathematically and with structure and behavior. So the collision is very complicated. It is not just a proton hitting a proton. It is a gluon hitting a gluon or a quark hitting a quark, and a lot of different things can happen. So again, you have 10 to the 8th of these things happening per second as well. So you have a lot of data to look through, and a lot of different particles that pop out that you need to detect. So one interesting event that can happen is, so first of all, when quarks hit each other, they can bounce off each other just like regular momentum, but momentum problems. But what happens is when a quark is pulled away from another quark, you end up getting hadronization. And so this is the concept that there are no such things as free quarks because the potential between quarks rises exponentially. So when you get these quarks that want to move away from each other, it's actually energetically favorable to create another quark-antiquark pair to couple with these instead of bringing these two back together. So what happens is you never find just free quarks hanging out by themselves. You always find hadrons. So that's called hadronization. And so these hadrons are very unstable. And so if we look back on the past slide, this black line just represents a hadron. And so unstable hadrons decay, just like carbon decays. It's unstable, has a half-life, but the half-life here is very, very small in comparison. So what happens is they decay, and we call the decay a jet. Okay. So jets are pretty much just sprays of particles. So you need a detector in order to detect all these different particles that pop up. So what I worked on again was the Atlas detector. This picture down here is just for scale. There's a very small person right there in comparison to the detector. And this actually isn't all of the detector either. You can see right here, these are the toroid magnets and these are the toroid magnets. So it extends farther back and front because you have extra detectors out here, and it extends farther out. So it's a very, very large detector, which I sadly did not get to see because it was running while I was there, and radioactivity is bad. So didn't get to go down there and do what this man was doing, but that's all right. Okay, so what we have are, so it's a cylindrical detector, and there's also a middle piece that's not shown here that you slide in, and that is this inner part right here. So you have a lot of different detectors in here that look at different particles, because particles have different properties. So this inner detector is called the pixel detector. It tracks position, very, very high precision. Yes?
Can you go a little bit slower?
Yes.
Sorry,
Thank
you're
you.
talking really fast and I'm trying to type it down.
Sounds good. Thank you for slowing me down. All right, so the pixel detector tracks position to very high precision. So what we have next is the transition radiation tracker, and then we have the electromagnetic calorimeter, which looks at charged particles and tracks their energy. We also have the hadronic calorimeter, which captures things such as neutral particles that pass through the electromagnetic calorimeter. And then we also have muon spectrometers, which are these big end caps at the end. And these capture muons that come out. And so muons, again, are very small particles, and they don't interact. They're very low interaction. So what we have out here are detectors that capture them because they pass through all of these inner detectors. Okay, so how does a detector figure out what we need to know? So first off, we need to reconstruct the path. So this is like the silicon detector. So what happens here is you have charged particles moving through. What the charged particles will do is, you can say this blue line is a wire. And so what the charged particle will do is, while it passes these wires, it ionizes charges on the wire and creates a current going through the wire. So if you think about having wires in both X, Y, and Z, depending on which wires have a current going through them, you can track its position in 3 dimensions, which is very nice. So that's how the position works. So you get X, Y, and Z. But what we want to know is the momentum and the mass of the particle, because that is where we get a lot of our discrimination between what particle is what, is these variables right here. So what we do is we use that position, and we use it to find momentum because the toroid magnets cause a magnetic field to go through the detector, which curves the path of the particle. So when you get these detections for position, you can use them in order to find the momentum. And this is physics 214, where you can use R, which is your radius of curvature, to relate the momentum. And there's R right there, to your magnetic field. Okay, so now we have the momentum, but how do we get the mass? So that is the calorimeter's job. So what a calorimeter does is you have a particle traveling a certain direction, and here's the detector. So what happens is the particle deposits its energy into the detector. So it's like shooting an electron at a wall and it hits the wall type thing. So all of that energy is deposited into the calorimeter, and you can use that in order to find what the mass is by E equals mc squared. So the concept here is very similar to solar panels. So solar panels, light comes in and it ionizes charges in a semiconductor, and you can use those to create current. Here, pretty much the same thing, except instead of light you have particles traveling through. And there you have the mass. So we have all this information about the particles, and there are, again, even more of these than there are collisions. So you have a lot of data going through. So this is kind of a funny thing from Wired magazine, where they created comparison between how much data the LHC gets, which is about 15,360 terabytes per year. And you can see YouTube's very close behind at about 15,000 terabytes per year uploaded. Another thing is this gigantic purple thing, which is all the business emails sent per year. It's very large in comparison. It's about 3 million terabytes. So if the answer to the universe is in here, I'm wondering what's in here. All right. On that note, we're dealing with a lot of data, so let me get to my project. So my project was finding B-QUARKs. So finding B-QUARKs is very important because if we're wanting to find new particles like the Higgs or detect more Higgs, the B-QUARKs are actually a direct product of a certain Higgs decay. So if we can find them, then we can backtrack that and find the Higgs. So what I was given to work with was data for this decay right here, which is a TT bar semileptonic decay, which I will explain. So what happens is you can think of this as the proton-proton interaction, where two quarks interact, produce a gluon, and then this gluon creates two new quarks, which are top quarks. And then these top quarks decay. So this is your shower you're looking at, or your jet. And so these top quarks decay into B-QUARKs. So B and anti-B are just two different types of B-QUARKs. And then these B-QUARKs also have jets. So another thing is you have a lot of background data, because there's interactions that you don't care about. There's particles you don't care about that aren't Bs. And you have to deal with that as well. So the data I was given was for a certain amount of time in the detector. It was about 654,000 jets were detected, and each jet had 15 or less tracks in them. And so the way we figure out these different variables, so we use these variables given, it's actually way too far than I wanted to go. So we use these variables here, which are given from the detector, in order to create discriminants, which are other variables that are combinations of these that are different for particles of different types. So we use those in order to create discriminants, which are these sets of variables. So I'll go ahead and explain what these variables are. So d naught itself is the distance from the primary axis. So you can think of this line right here as the axis where the protons are moving prior to collision. So this is the z-axis here. It's the distance from a certain particle, or the track of a certain particle, to that axis. And z naught is how far away it is from the collision point in the z direction. So this would be the primary vertex where the collision actually happens between the protons, and then z naught is their distance in this direction away from it. So S d naught and S z naught are d naught and z naught divided by what's called its significance, or how likely it is to be a track that we're interested in. All right, so we also have jet PT, which this one's a little more interesting to explain. So when we talk about jets, we talk about sprays of particles. So what you're actually detecting is all those different particles within a certain jet. So what jet PT means is if you sum all those momentums of the particles that are in a certain jet, you get the jet momentum. So it's kind of working backwards in time. So you're collapsing all the particles that were in a certain jet, or all the tracks, into just one entity itself, called jet PT. All right, and track quality, yes.
Does the T stand for total?
Sorry?
Does the T stand for total? What's the T?
Oh, yes, thank you. The T stands for transverse. So it is all the momentum that would be in the XY plane. So we don't care about any momentum happening in the direction of the proton-proton collision.
So, if I may,
Yes.
a model, so we don't care in the direction of the proton-proton collision. So if I made a mental model and I said I've got a pool table and I throw a billiard ball from above onto the balls and it sprays them out. PT is the measure of the total momentum of the big spray of jet you get because of that collision.
Yeah, you can think of it that way. And the reason we don't care about the other direction is because if you don't have a collision, a lot of the times they're just going to pass each other or be just slightly deflected. So that is a high amount of background that we don't care about. When you have a collision, you have a high amount of particles moving in the transverse flow. So that's why we look at the transverse flow, because it's a higher number of collisions per data you're actually tracking. So another variable we look at is track quality, which is, it's pretty much a discriminant that tells you, I think it's how likely the track is what you're looking for compared to the background, which is kind of a ratio between signal to noise. You can think of it that way. All right, and then PT frac and DR. So PT frac is transverse momentum, but the fractional transverse momentum. So that is, if you look at a certain jet and a certain track going through the jet, it's the momentum of that track divided by the momentum of the jet in total. So you can think of it as how much of the momentum a certain particle carries off from the jet itself. So this is a picture of a jet. So you think of about a bunch of particles coming out of here. It's one of the particles' momentums divided by the summation of all the particles' momentums. And dr is your opening angle of the jet. So pretty much how you can think of it is if you have a particle going this direction and a particle going this direction, and that's the farthest or the widest spread of the particles, you can think of dr as your angle right here between the farthest particles that are actually within your jet. So it's an angular distribution. Okay, so how we actually use these discriminants, or how we get these discriminants, is through computer algorithms that get the data from the detector, so your momentum and your mass, and spit these out. Okay, so we have a lot of different algorithms that CERN has used. What I'm working on is an RNN, but I will describe the process of getting to where we are today. So SV1 is an algorithm that fits the secondary vertex. So the primary vertex here is where the protons collide. This is the secondary vertex, and that is where the B hadron becomes a jet. So what the secondary vertex does is it pretty much creates that cone that was on the past slide and figures out where the origin of that cone would be, and that's your secondary vertex. Okay, so JetFitter, what JetFitter does is it doesn't only look at the primary and secondary vertices, it looks at the tertiary vertex. So what can sometimes happen when a B jet decays is it creates a D hadron. And so a D hadron has a very similar mass to a B hadron, so it's going to follow the flight axis of the original B hadron very closely. There's minimal difference between where the B hadron's going when it decays and where this D hadron would go. So D hadron is just a hadron, which is a combination of two quarks composed of a C-quark. So anything with a C-quark. And that creates a tertiary vertex because the D hadron's also unstable and creates another jet. So what JetFitter does is it looks at this whole chain and fits this linearly instead of just this. So JetFitter is a lot better at actually finding secondary vertices because the only time you have this kind of linear thing between three different vertices is when you have a B hadron decaying to a D hadron, but it doesn't account, or it doesn't count as many as SV1 does. So SV1's not as good at counting how many B hadrons you have, but JetFitter only counts the ones that have this tertiary vertex, which is not all of them. So you're getting less of the actual B jets when you use JetFitter. Okay, so another algorithm is IP3D, which is the three-dimensional impact parameter, and what we mean by impact parameter is just SD0 or SC0, so your distance parameters. So what you do is you look at one of the parameters versus the other, you create a distribution out of that. So how many particles have this SD0 and this SC0, and then compare that to a theoretically calculated distribution, and then see how your data fits it. Okay, next one's MV2. So this one is actually a neural network, which I'll explain. And pretty much what a neural network does is it takes multiple inputs, and creates outputs from that. So what the inputs are for MV2 is actually the outputs from IP3D, SV1, and JetFitter. So it pretty much gets all the information from the past 3 algorithms put into one. So it's very good. What we're trying to do is improve on that. So instead of doing a neural network, what we want to do is a recurrent neural network. So I'll explain that in a second. Here we have a table of all the different inputs and outputs for the different algorithms we're looking at. So summation of all of what I just said. So we're going to skip past that really quickly and talk about neural networks and recurrent neural networks specifically. So why do we want to use recurrent neural networks instead of neural networks? Because we already have MV2, which works fairly well. So recurrent neural networks have easily adjustable parameters for different data. They take into account correlations between tracks. They're easy to extend to more input variables, which is actually one of the big things I was doing, was trying to add more input variables to the current recurrent neural network that we have. And compared to IP3D, IP3D actually assumes no correlations between tracks, and the templates are built from a training sample, so the probability distribution function, the data is directly compared to the template. We can skip past that for now. Yes?
Michael, could you just briefly discuss, or do you have some experience with other places people are using neural networks or recurrent neural networks?
Yeah, so neural networks are used for handwriting recognition, for example. So we'll go through this in a second. Thank you. But I'll actually go to the next slide, because it is talking about recurrent neural networks. So recurrent neural networks are used for handwriting recognition, speech recognition, and a lot of other things. So pretty much what a neural network does, before we go into recurrent neural networks, is it takes data that has a known, it takes data that has a known pattern to it. So speech, for example, it gives it what the actual speech is, and then what you do is you train it in order to look at new data and do the same thing to what the data is that you trained it on. So I will talk about this, how that works itself, but those are some examples.
So Siri and Cortana and people's voice recognition.
Yes, those work on machine learning algorithms like neural networks. Yeah. Okay, so recurrent neural networks are neural networks that iterate over time. So what you have is, these are all the different input values. So you can think of this as all the different outputs that come from your detector. So like px, py, pz, and mass. And then what you have is, for each discriminant you want, you have a different node, what we call hidden nodes here, that get input from all the different variables. And then weight it accordingly and output the discriminant that you're looking for. So the discriminants over here would be the outputs, which are the SD0, SZ0, PT-frac, and the rest. So for each of the outputs, you need one hidden node per each. All right, so what do I mean by iterating over time? Well, let's do some math. All right, so what happens is you get inputs from the first layer, which remember from the detector. So what each node does is it takes a weighted sum of the inputs. So if you just look at this first term here, x is your input. What you do is you put a certain weight to each input. So say you're trying to find the position of the particle. That would be different than trying to find the momentum of the jet, so the weights would be different for different inputs. So for the momentum, you would put a high weight on the momentum inputs, maybe a lower weight on other inputs. But if you're trying to find position, these weights would be different. So what you do is you do a weighted sum, so you start adding all the weights together multiplied by their inputs. But with a recurrent neural network, after you do the first iteration, you have iterations from the past node itself. So that signifies these arrows that are outputs from the node, but they go back into the node. So what you have is these Bs. So your B is called your final activation. Pretty much what happens there is you take some function and use it on the AH, which is the weighted sum of the inputs. And so what theta pretty much is a function such as hyperbolic tan or the logistic exponential. It pretty much restricts your data to a certain range. That's the main point of it. So hyperbolic tan will restrict any value. So any value given is this line to a range between 1 and -1. Logistic exponential will restrict it to 0 to 1. So it just makes your data easier to work with, and these are monotonically increasing functions, so it doesn't change what your data means as well. So these B's, which are pretty much restricted versions of A's, go back into your new inputs as well. And so what this is your actual output on the nodes on the far right, which are the discriminants. So yeah, what you do is you sum all of your outputs of each of the A of H's. All right, so that actually gives us our discriminants. But how do we figure out that these are the most likely values, or the values that we want that actually describe our data? So the way we do that is we look at the backward path. So instead of going forward in time like we were doing, now we look at how it changes backward in time. So what we define is a loss function. So I'll describe what this means. So first off, this pi is the multiplicative sum. So instead of adding things together, you multiply everything together. And so what this term is the probability of something given something else. So what we're looking at is the probability that, say, a track is a B-QUARK instead of a top quark, given the information of the input variables that we get from the detector. And so we take the natural log of this, which again is just changing our data to restrict it to a nicer set of numbers. And this negative is actually very important. The negative's there because what you do with the natural log, and I'll actually draw this, this is probably better to have up on the board. So the natural log, as it goes to 0, diverges to negative infinity. So if you take the negative of that, you get this. So what's important about this is the negative's there because you want things that have a very small probability to have a large weight in your loss function. So this is your loss function, and this is some variable. So if you have something that has a very small probability of actually being a B-jet, or a B-track, it constitutes a large amount of your loss function, which that's the definition, is the loss function. So it's a flip of, yes?
So this is the part of the algorithm that's fitting into a known pattern. Like if it's analyzing speech, this is the part where it sees a phrase that it thinks might say, but apple, and then is like, no, nobody ever says but apple.
Yes,
like,
yeah.
Okay.
Yes, you can think of this function as that, yeah. And so what we want to do is we want to minimize that function. So we're trying to converge to something that actually is what we're looking for. So what we do is we look at its derivative with respect to weights. So remember, the weights are, these are numbers we actually put into the algorithm, which multiply numbers that go through the algorithm. So these are these W's. So these weights are very important, and they're actually the key to how these machine learning algorithms work. So you want to minimize your loss function with respect to your weights. So pretty much how that works is you throw a weight into your algorithm, and you try and find where the loss function is such that your weight gives the smallest loss function. So let me also draw this. So say you have a loss function that looks like this. We'll just cut it off there, per se. So say this is your loss function. So what you want to do is find minimums. This is calculus. So if you want to find a minimum, you take the derivative, and we'll usually set it equal to 0, but a lot of the times we don't know what this is analytically, so we can't do that. So instead what we do is we pick an omega. So let's call this our weight that we just choose, okay? So that corresponds to this on the loss function. So if we want to minimize it, what we want to do, this is the computer science of it, is we want to move towards where our minimum is. Or this is a minimum, or local minimum. So what we want to do is move in that direction. So what the algorithm does is it looks at an interval around omega and sees what the derivative is. And wherever, so if the derivative is negative, it moves in the direction where the derivative is negative. So what it would do here is it sees if I move to the right, I go lower on the loss function. So we want to minimize our loss. So we go that direction a certain step in omega. And if we continue to do this, we'll hopefully get to where we want to be, which is at a minimum. Remember, this isn't the global minimum, so this isn't the best fit, but this is a fit. And so it's good that we can get there, but we want to get to the global minimum. So what we do is we add this extra term in our delta omega. So delta omega is usually just some fixed number that's proportional to how your L changes. So it's how the derivative looks, pretty much. But if we add this extra term, which is our momentum term, if we move a large step in delta omega, that's going to add to our next step as well. So it's kind of a nice little trick, but pretty much what you can do is, so you have a large step in delta omega here, that means the next step is also going to be large because of this equation. And the next step will also be large, and eventually you can go over that and converge at the global minimum. It's a little trick you can use. You can think of it as momentum, like a ball rolling down a hill type thing, right? So if the ball didn't have momentum, it would just move at a constant speed and then converge here. But if it had momentum, it would continue moving and then hopefully get over that hill. So that's the comparison here as to what we're doing. Okay, so one more thing. So these nodes that we're looking at, these hidden nodes, are not just, so the ones I was using at least, weren't just as simple as you weight it by one thing and it goes back into the algorithm. They are actually long short-term memory nodes. So I know this is a complicated slide and there's a lot going on, but I'll hopefully explain it. So one thing that happens when you just iterate over time steps is that, say this is an important piece of information that goes into your node. As you continually weight it, the significance of that goes away. So you can think of shading as significance. So if you continue iterating it, this information will leave, but what if it's important information? What if it's something that this new piece of information in there can use to better characterize what we're looking at? So very complicated. I know there's lots of arrows here, but pretty much what we're doing is replacing each node with this set of nodes. So the most important part of it is the forget gate, because if it's not important information, or if it's information that says that doesn't look like a B-QUARK, then you get rid of it. And so you have high weighting on the forget gate. And so if it's an important piece of information, then you have, or sorry, the flip. If it's an important piece of it's an important piece of information, you have very low weighting on the forget gate because you don't want to forget it. So what this replacement does, which is very nice, is if you have an important piece of information, it survives over multiple weightings because of this complex nature of it. So this is what we actually use. So, okay. All right, so on to how neural networks actually work and how you get them, yes?
In the bottom left here, did the forget gate forget it for the last interval there?
Yes, actually, thank you. Yeah, so this is actually where the forget gate has 0 weight, or complete weight. So you completely forget it, yes. So it's not there anymore and it moves on to the output gate. Yeah, thank you. Okay, so onto how neural networks actually work. So remember, we want to find our lowest weights. So how we do that is we work with data that actually has known patterns to it. So it's simulated data, so we actually have all of the tags that we want. So we know which particles are B-QUARK, which particles not. And so what we do is we throw that data that we know, what everything's tagged as, into the algorithm and let it iterate over time, let it converge, and see how it looks to our known data. Because remember, simulated data, we know everything about it. What we're trying to do is train it so that when we put actual data into it, we can trust it. So yeah, so it compares the classification of a set with known classification from the simulated data. So what you can think about is the errors that you get are then fed back into the network and you modify the algorithm iteratively. Okay, so this algorithm is fitting your data. One important thing that happens is if you continue doing this, it sounds like as you continue iterating, it's going to get closer and closer and closer until your errors are about 0. And that sounds great on the face of it. But if you look at this is a set of data points. And so your first iteration will maybe come up with a linear fit, which looks pretty good. I mean, I like the linear fit. But if you continue iterating it, you'll get these errors here to go to about 0. And your final iteration will look something like this, which has 0 error. Sounds great. But if you look at a new set of data that looks like this, you'll get some points in between, probably. And then the errors are very large. So it looks great on the outset, but when you put actual data into it, it's a terrible fit. So this is where the true performance and the training performance diverge, is at some point. So what we do to figure out this point is we, instead of throwing all of the simulated data into the algorithm, we say throw 90% of the data into the algorithm, set 10% aside, so that once the data is thrown into the algorithm and it iterates, it looks at the 10% you set aside and says, okay, how is my error changing over time? And so if your error is getting bigger over time, then that's the point where you stop the algorithm from working. So this is a big problem. It's already been fixed, thankfully, but that is something we need to look for, is overtraining. Yes?
So when the algorithm is like learning,
Yeah,
it's
finding the
figuring
lowest.
out what weight to apply to data of certain types. Is that
Exactly,
correct?
yeah. So what we're throwing into it is data that's simulated data from the decay that we're looking at. Yes. So yeah, it's
Figuring out if the data looks like this, don't forget that because that stuff's important.
exactly, yeah. Okay, so if you end up using recurrent neural networks to get information about B-QUARKs, what's nice is you get more B-QUARKs and you get them correctly tagged. So if you look at this graph up here, this is B-jet efficiency, which is the efficiency of your algorithm to actually tag B-jets, versus non-B-jet rejection, which is things that aren't B-jets, which you want to reject. You don't want them as your data, you only want B-jets as your data. So past algorithm that was used was IP3D, which is this curve right here. And so if you just look at the red line right here, this is RNN. And what's nice is the area under the curve pretty much represents the amount of B-jets that you found. So the more area under the curve, the better. So what we can see here is that using RNN instead of IP3D, we end up getting this sliver more B-jets than we had before, which is equivalent to about 1.5 times the non-B-jet rejection and about 8% more B-tagging efficiency. And so if you plot this over different jet PTs, so about how much PT each jet has, you can see that between the black and the red is constantly higher than the black, which again means more B-jets that we're actually tagging correctly compared to the past algorithm that we've been looking at. All right.
So Michael,
Yes.
these are your results. So far you've told us about the background in particle physics, and then in sort of your computer science that you learned about particles and that's applicable to neural networks more generally. But here it's physics, right? And by pushing this line, this is a successful summer then, right? I mean,
Yes.
even
Yeah,
just
this
now,
sliver means success.
Yeah.
Yeah, when I saw that, I was very happy. Very, very happy. And this sliver too. Both of them were very good. Very good slivers. Okay.
What are the green and blue?
I will go over that
Okay.
later. Don't look at this.
Okay. You got it.
Okay, so one thing I did was, this is a new algorithm that is looking at data. So when we get distributions, we need to figure out why they look the way they look. So one thing that is physically interesting is that, so SD naught is, again, your position of your particle, or of your jet. So what's interesting is it favors positive SD naught, which is different than what you would expect. You wouldn't expect there to be some sort of more jets over here on this side of the primary axis. So this is the primary vertex. You wouldn't expect there to be more jets over here than over here. That doesn't make sense. By symmetry, they should be the same on both sides. So what's interesting here is you have this positive tail. And so trying to describe that was actually kind of hard. But if you look through the code, what's interesting, I'll actually have to draw this too. What's interesting is that in the code, positive SD naught is actually favored compared to negative SD naught. So if this is your primary vertex and this is your secondary vertex, so this is your jet, all the different tracks coming up. So what positive SD naught means was that, so say this is a certain track in your jet, right here. So what positive SD naught means, this is the definition of the positive and negative version of this, is that it passes this linear line between the primary vertex and the secondary vertex on the side that the secondary vertex is actually on. So now it makes sense, because if a track is in this jet, it should pass, hopefully, over there if you extrapolate it backwards. So you detect it up here, you extrapolate it backwards, and it passes this line on the positive side. So what negative SD naught means is it passes this line back here, somewhere back here, which could happen if you have a track, say, that looks like this, and you detect it over here, it looks like it's in our jet, and it may well be coming from a decay right here, or something that comes back. So, but it does make sense that more tracks would pass on the same side. So this positive tail is actually a good thing. Looked weird at first. Okay, so another thing is we look at different discriminants that come out. So here we have discriminant called PT-FRAC. And what we can see between B tracks, light tracks, and C tracks is that these distributions look different. So B tracks are from B-QUARK, C tracks are from charm quarks, L tracks are from any other type of quark that's not a B or a C. So you can see here that these distributions look different. We have a B distribution that peaks at a lower value than these two. So what we can conclude here is that if we can actually use this information, we can discriminate between B's, L's, and C's. So that's what we try and do. And so these three are so what we have is we have the distributions plotted for B's, L's, and C's, and then the distributions after that data has gone through these different algorithms. So you can see here that B's, they all fit fairly well. But what's interesting are the L's and the C's, because we have algorithms that do not follow the B distribution, or the L and C distribution, which is very different. So this is something that I will come back to in a second. But first we need to explain why this looks the way it looks, because we have B's peaking lower than L's and C's. And this is actually due to the decay chains for B's, so all the different possible things that B's can decay into. So primarily, a B hadron decays into what are called B plus and B naughts. 40% of them decay into that. So if we look at what B plus can decay into, for example, we have this long list of things. And we also have a D in there, which can also decay into a large amount of things. So first thing you can conclude here is that compared to light jets, which have much less constituents, we can make sense of this graph, which is the number of tracks per jet. What we can see right here, especially because this little guy right here can go into many more things, is that we should have on average more tracks in B jets than we do in L's and C's. So that's why this peaks over at about 8, whereas this peaks at about 6. Okay, and going back, this distribution right here, we have a lower fractional momentum. And so what that is consistent with is all of these very small particles coming out. If you remember, electrons and any kind of lepton and neutrino are very small in comparison to things like this. So they will go off with a very small fraction of your momentum, especially because this is about the same mass as this. So this will carry a lot of the momentum, whereas these will not. So that's why B's peak at a lower momentum. All right, so one other variable that we were looking about adding. So hold on really quickly. So what we had discriminant-wise prior to me coming in was SD naught, SC naught, jet PT, and track quality. We wanted to add more to that. So what I was thinking of doing was looking at PT-FRAC, which thankfully there's a difference, so we can use that as a discriminant, and DR as new variables that we can add. Because recurrent neural networks are very nice because you can easily add more variables to your list. That's fine, it can take that. It actually usually helps when you add more variables. So when we look at DR, which is again the opening angle of the jet, so pretty much how wide this jet is, we can see that between B's and C's, you have a very close form, but between L's, it has a lot less at this certain value of DR. And it has more over here. So this is, again, another thing that we can probably use to discriminate between B's and light quarks and C quarks. So again, if you look over here, we have different distributions for B's, lights, and C's. And one important thing that is in these three and also in the past three is that if you look here, so the RNN is what we're concerned with more so than anything. If we look here, the black line is the actual L tracks, and the red line is what RNN thinks is L tracks, and same here for C's. So what we can see, and this worried a lot of people that were in my group when I first showed this, was that this does not look like this. And same for here. So didn't think that was very good at first, but in the end, this is actually a very important outcome, because what the L's and the C's are showing is that so these distributions are for a specific decay chain. It's the decay chain I showed in a past slide. What we want is an algorithm that works for any decay chain, because we're not just going to have that specific decay happening. We're going to have a bunch of different decays happening. And if we're looking for the Higgs decay, which goes to B-QUARKs, which is one of the most important, then we don't want an algorithm that looks specifically for this decay. So what's nice about this is that the distribution looks the same no matter what decay we're looking at. So even though the C's and the L distributions are different, the R and N distribution is constant throughout. So that is actually a good thing in the end, because we don't want our algorithm to be event topology dependent. We want it to work the same for whatever kind of decay we're looking at. So that is a very important outcome. All right, and one other thing, if we look at the JET-PT distribution, oh man, I'm running out of time. If we're looking at the JET-PT distribution, all the algorithms actually work the same for this. So one thing is, when you're adding new variables to an algorithm, you need to be careful, because some of them may be correlated to past variables, and you don't want that happening. So if an algorithm is correlated to a past variable, when you train on it, it's going to doubly train on that specific variable that it's correlated with, because you're training it on a variable, and then you're training it on another variable that is pretty much the same variable, just maybe multiplied by a different constant. So you're doubly training it on that, so your algorithm is going to cut off early, and you're not going to get the nice convergence you look for. It may converge right here instead, because it's doubly looking at a certain variable. So it's important to look at correlations. I'm not really going to go through this slide because I don't have time. So one conclusion we can come through to by these graphs, so what these graphs are distributions of PT frac versus different variables. And so what you're looking for are correlations between variables. So like if one thing increases and then on average the other variable decreases, that's a negative correlation. And if one thing increases and the other increases correspondingly, that's a positive correlation. So what we don't want are things like that in our data. So what we can see here from all these different graphs is that thankfully PT frac is not correlated to any of them, and it's mildly correlated to jet PT. So we can see a little negative line right here, but as you get to smaller PT frac, you can see it kind of muffles into noise. So we don't have correlations. We only have a light, mild negative correlation for large PT. So we can use this. One thing that came up that was a big problem was that DR is actually correlated to jet PT. And it's negatively correlated over a wide range of DR and jet PT. So this is a problem. The way we proved it was looking at, so just take into account a two-body decay, and you look at all momentum and energy conservation rules, so a lot of physics going into here, but you eventually get this equation relating your opening angle to your momentum. And if you Taylor expand this, about dr equals 0, and you would Taylor expand it about dr equals 0 because your momentum is so high that your jet does not actually look like this. If I drew a jet as it actually would look, it would be something like this. You have a very small opening angle usually. So if you approximate it about dr equals 0, you end up getting a nice linear correlation, actually not nice, between dr and pt. So we can see that to the third order, dr and pt are correlated, because if dr goes up, you can multiply pt over here. Pt has to go down to keep 2m constant. So we have a correlation between the two of them, which is not good. But one thing that's interesting is that we ended up accounting for that. So this was very cool. This is a very cool computer algorithm thing that happened, was that we reweighted it each time it iterated. So each time it learned about both dr and jet pt, we pretty much weighted it so that it was weighted half. Because remember, if you learn both, you're learning doubly, or on the scale of 2m. So if you scale it back, then it's like learning it only once, but you still get all of the discriminatory information from dr and from jet pt. So now, really quickly, looking at the color graphs that I was asked about before. So the red is IP3D, the brown is just RNN. Now if we add PT-FRAC and DR, we get yet another good sliver. So we get more jets now compared to orange and brown. And another thing that was actually very interesting that I did not have time to figure out, because I only had 8 weeks there, was that when you reweight the jet PT and the DR, like I was talking about on the last graph, you actually get less jets in comparison. No, actually we did figure this out. And that was because of event topology. Because if you don't reweight, then it'll learn the event topology very well, but that's not what we want. We want it to learn all event topology. So it's worse at detecting this specific event, but when we used it on other events, it was actually better than this prior. So conclusions, we found a new algorithm that's good at finding B-QUARKs. And we added PT, PT-FRAC and DR as new variables. Despite DR being correlated, we still accounted for that. And we got more B-jets than before. So I want to give a really quick thanks to everyone at CERN. So my 3 advisors, Zihao Zheng, primary advisor, Lauren Tompkins, Michael Kagan. Thank you, Tara Shears, for giving me some slides about particle physics that I used at the beginning. Thank you, Professor Yongxing Gao, talking to the camera at this point, I guess. Thank you, Professor Yongxing Gao, for taking having the particle physics class with me and accepting my application and setting this whole program up. Thank you, Dr. Lynn Kaminski, for telling me about the program. And also thank you to a peer of mine over at CERN, Jimmy Gonzalez, who I threw a lot of these ideas off at. And thank you, NSF, for the funds. Thank you, CERN, for putting up with me. Thank you, Fresno State, for the class. Thank you, Sonoma State, just because I have to represent. As a really quick aside, I was asked by Dr. Gao to show pictures of me working and me traveling around Europe afterwards. So, yeah, there was lots of coffee involved. Lots of coffee.
Wonderful talk. Really a fresh view of recent research and of, I think, tremendous growth. The particle physics part you talked about at the beginning, you picked up at this class last fall. Yeah, and then all of that programming and all of that neural network stuff. You developed your understanding of it for this project, right? So we're going to take a very short, like 90-second break for those of you who can't stay for the full question and answer session. It's only going to be till 5:15 that we'll do questions. But I know some of you talked to me before about a conflict. So if you could just please leave quickly and quietly, and then we'll continue with questions. All right, we've settled down here. Let's go ahead with our questions.
Yes.
If you guys were going to add another discriminant, was there talk about what you would do next after the GR and the T-FRAC?
Yeah, so there was talk about a new discriminant that is actually not based on, it's something that he kind of had a wild idea about that was like, if I have time, we could do it. So yes, there is one, but I'm not sure if it actually worked or not, because it probably worked on it right when I left.
Gotcha.
Yeah. Yes.
So these particles are traveling close to the speed of light, right?
I think it's 0.99999.
Yeah, it's MC squared, but that means it's relativistic speeds.
Mm-hmm.
That's pretty good.
Yeah, so whenever you try and diagnose this theoretically, you need to use relativistic kinetics. Yes, very much so. So it'll be very far off.
So like I'm dealing with hundreds of billions of seconds right here.
So in the neural network, trying to wrap my head around this, is it? It's not really rewriting itself. It's just coming to understand better what these weight parameters are for certain types of data based on what you tell it it should be seeing, right? Can you talk about that a little?
Yeah. So yeah, pretty much what you're doing is you input data into your algorithm, and it's going to iterate and get closer to your actual value that is minimizing your loss function. So remember, your loss function has to do with the probability of it actually being a B-jet. So if you minimize, or it's the negative. So It's the flip of that. But minimizing the loss function gives a higher probability of it being a V-check. So every time you move a certain step, you put more data back into the algorithm as well. So what you're doing is you're pretty much testing on it and saying how big are the errors now, and looking at, if the errors increase, then you need to stop it at that point. So what those arrows mean are, just movement of data pretty much from one step to the next. And so you're constantly outputting as well. Actually, I should probably go back to that. Because you're constantly outputting data as well. And so go back. So you're constantly outputting data. So you're getting new output. So the output is rewriting itself. But inside the hidden node, you're actually getting all of that data and it's compounding on itself. So what we're looking at here, I didn't explain this, so thank you for asking, is this set. So this is what the actual node looks like. So you're storing information in the cell, and the new information comes in, and it's weighted due to what happened previously. So, is that okay?
It's like now this is more likely based off of what you now know.
Exactly.
This previous node is becoming more likely because there's no better option that was seen in this last run.
Mm-hmm.
Okay. And you have to give it some data which defines the pattern it's looking for to start with.
Yeah, so that's the test data. So we throw simulated data, because everything has a tag in simulated data, because you simulate it. So you know which in the simulated data is a B-QUARK isn't. So you throw that in there, use it to characterize your lowest omega, and then throw real data into it, and depending on how it worked on simulated data, you can characterize it statistically how it works on real data.
So when Google's doing this, they're throwing in like 1,000,000,001 books, and
pretty much.
it analyzes this is how humans actually write or talk.
Yeah.
And uses that as its test data.
Mm-hmm. Yes.
So for your calorimeter, did you guys just shoot? What did you guys use for that? Like
For the
what
calorimeter?
particles? Yeah.
Coffee cup.
Coffee cup calorimeter. That's funny. And you're in chemistry too. Oh my. Okay, so for the calorimeter, what you're using is, it's actually pretty complicated. So it's usually some dense material so that when a particle encounters it, it will interact with it and deposit its energy into it. But at the same time, you need to, because remember, you're using the same kind of detector to measure position as you're using to measure energy as well. So you divide it up into layers in different directions. It's kind of like a CCD. It's like a camera. So it captures light coming from different areas and then puts them together into pixels. This is the same thing, just with particles instead of light.
And you said that it absorbs the energy of the particle?
Yeah.
So how does that work, and what happens to the particle once the energy is absorbed?
So, that's a good question. So a lot of the times when a particle deposits its energy, it doesn't deposit all of its energy. So you need to account for that as well, because a lot of the times, so if you think about a particle coming in, it's very, very quickly decelerated. So when you decelerate, especially a charged particle, it will emit a bunch of light. So a lot of the energy is actually coming off and not being captured by the detector. So to do that, there's some algorithms in quantum chromodynamics and electrodynamics that take account for that, depending on the size of the detector and different things like that.
And so you can't detect the light that's coming out of the particle decelerating?
I believe you can. Yeah. I believe so photons are detected in a different part of the detector, but if you look at, you can say like backscattering photons, you can detect those as well and account for that.
Do you get like all kinds of photons? Like all different wavelengths?
Yes. Definitely.
So it's a rainbow? Is it a rainbow cannon?
Dr. Shi.
Yes, I think it's wonderful to see that a student like you can do so many things in just like 8 weeks or 9 weeks. But I just wonder, other than doing this, heavy physics or computer science related project, how does CERN train you guys? What's your daily schedule? Weekly schedule look like? How often do you meet with your advisor? And how long does the training take? And how do you know that you're actually heading in the right direction?
Lots of good questions. Okay, so everyone had different interactions with their advisors depending on who their advisor was. Mine was the type of advisor that would meet with you for about 5 minutes per week and look at your data and give some random shout outs like maybe you should try this, maybe you should try this, and then leave you to do your work on your own. Because he had a bunch of different things going on, was constantly gone. He was gone for the first 2 weeks I was there, so I didn't get to see him much, but he pretty much just kind of showed me in the right direction. It's like, have fun figuring this out. Other people met their advisors like daily, per an hour a day, I think was the most that someone met with their advisor. And training-wise, what happened was, well, you take the particle physics class, then you take an intro class the next semester about the computer's algorithm, or the computer programming language that they use. And then usually the first 1 or 2 weeks, they just throw a bunch of books at you, tell you to read them so you can get the background you need, or take another online course, but this time intensified, in order to learn it within the first 2 weeks so that you can actually start working on the third week. That was the goal of most advisors. And working-wise, most of them expected you to work about 8-hour days. All of us were pretty motivated, so we ended up working about 12-hour days most days. It's about 9 to 9 was everyone's regular schedule. And we kind of helped each other with that, so that if we saw someone going to dinner at like 7, we'd be like, hey. And so it helped to have peers. Yeah, exactly. It helped to have peers that were just as motivated to keep you as motivated. And also about a third of the way through, the CERN Summer Student Lecture Series started, so that took 3 hours of our day from 9 to noon, which was a great lecture series, by the way. And I think they have those online. I don't know if it's public, but I believe you should look them up if you can. And so that took about 3 hours of our day, and then we were still expected to work 9 hours. So we had to do that after, lecture. So it's intense, but I mean, most of the time, if you want to, you get the weekends off, so you can go hang out and travel and eat.
Catch up on those meals you're not having between 9 and 10.
Exactly. Yes.
You said there's 10 to the 8th collisions per second. I'm wondering how were these sequential in time? They weren't overlapping in time because they happened in like picoseconds or something? Or
So-
how do you know you're not looking at 3 collisions at the same time?
Yes, yeah. So that's another thing. So that has to do more so with the speed of the detectors, because these detectors have to look at like picosecond intervals between interactions. So 10 to the negative 12. Yeah. So what you do is you kind of average it. So you look at your particles coming out, and you backtrack all the spray of particles into quarks, and then you see how many quarks you have. And it should be like 2 or 3 interact, and there's some probability distribution that you come about quantum chromodynamically from that, and you average it out over a very large time interval. Yes. Yeah. So I think I'm not sure where they got that number from, but I believe they looked at it for a very long time, and so they could get a precise number of actually how many collisions were happening per second. Yeah. And I think it was over a whole run, and they run it, I think, like in yearly or 2-year intervals, I believe. So they looked at it over a whole year as well. So it's approximately the right amount of collisions because of such the long time interval that we're averaging out.
But the instrumentation is doing it in picoseconds. So most of the events you're looking at are a single collision. They're not 2 at the same time.
So when you backtrack it, you get the number of quarks that are colliding. And so that number is definitely greater than 2. So what you do is you get the distribution of how many quarks collide on average between them, and then divide that by that. So you get how many collisions you have. So like your number of quarks divided by, your number of quarks per collision gives you the number of collisions. And then averaged over a long time gives you the approximate number of actual collisions per second. Yes?
So you said the quarks are the ones that are colliding, not the protons that you put into the accelerator, right?
So quarks are what protons are composed of.
Right.
So you don't even have to think about protons in general, because protons are this abstract object that we thought was elementary, but now we know that quarks are elementary.
Right. And there's 3 quarks per proton.
Yeah, 2 ups and a down.
So like, can those quarks like exist on their own, or are they like these 3 like?
Bounded states, yeah.
And
So
then
it's
they-
like hydrogen. You have a bound state between them. But this time when you try and pull them apart, there's not one point where they actually come apart. There's a point where they hadronize and form 2 different hadrons. Yeah. Yes?
So
I can't quickly and easily do math off of 15 terabytes a year, but about how much data are you getting per second of collision?
Good question. I don't know that number off the top of my head, but 10 to the 8th collisions per second, that's actually the number detected. So
About how many bytes is each collision, for example?
I don't know that one.
Yeah.
It also depends on average how many particles it decays into.
Yeah.
Because if you have a large number of particles, then that's a large number of detections. But sometimes you don't have a large number of stray particles.
Yeah.
Yes.
So quickly, there are like about pi times 10 to the 7th seconds in a year. So if you're getting I don't know, if you're getting, if you were getting 3 times 10, or you're getting close to, you're getting 15, but let's round it to 30 because I'm an astronomer, right? So we'll do 3 times 10 to the 13th approximately, and you have 10 to the 7th, 3 times 10 to the 7th seconds. So what did I just say? 13 and 7, so about a megabyte a second, I think is what we're talking about. With that, I hate to do this. There are more questions, but we should take them offline as we're ending up the period. But let's thank Michael again.